Hello everybody and welcome to the second video of our linear regression part of our machine learning course, and we're gonna go on and learn more about linear regression, where we use multiple variables, not just one variable, to predict, to fit our data. And we're gonna use gradient. We're gonna know what's gradient descent for multi variables. If we use multi variables, that means we need to change a little bit our gradient descent. We're gonna learn what's polynomial regression and what's normal equations. So for multivariate linear regression, we want to use more features to be more precise to predict our data. For example, in our house costs example, we can use the size, the location, and the building date of that house to predict the cost. So yeah, the old hypothesis function was only about one variable, so it was w0 plus w1 x. But now we have not just one x, we have multiple x's. So now the new hypothesis becomes f of x. This x is not just like one x of them. It actually represents all the x's together. So you can imagine like big X. So equals W0 plus W1 X1, exactly like we saw here, plus W2, which is another parameter, multiplied by the second, the second variable. For example, the size here, X1, the location is X2, and the building date, which is X3. So different variables, and also for each variable it has its own proper parameter, which is w. So the w3 for x3, w2 for x2, and w1 for x1, and w0 always there to make it a good linear function. So let's call w0 what it is. It's a bias. It's called bias. What do we mean by that? You know, like here we are trying to associate like parameters for each variable we have, but for our in our examples, we might like in real life, not all the prices of houses actually depend only on the size, the location, and building date. Sometimes it depends on the mood of the seller or something like that, like something we cannot expect, like something that's gonna bias our results. So that's why we call it bias, and we refer to by B. So from now on, we're not gonna say W0. We're gonna say B, bias. Except in gradient descent, like we're gonna calculate the W0 with all the W's, like the bias with all the W's. So we're gonna learn all of these parameters. So this bias is no special because it's gonna be learned with all the other parameters. So do you remember our friend Mr. Transpose that we learned in linear algebra chapter? So in the new hypothesis, we can use the transpose like to make our example as like vectors. So like vectorize everything. So it becomes like x transpose multiplied by w. The w here represents all the w's together. The x represents all the x's, and the w together, of course, excluding the w0. The w0 becomes b. So x transpose w plus xb. In many occasions, like many textbooks, you might see that here it's wx, like w transpose x. It's right. but in like when we are going to like program this, it's actually we're gonna program it for x transpose w, not w transpose x. So actually I thought this is better because it's more practical to do. So gradient descent for multiple variables. Of course we use gradient descent just for two variables, and now it's for multiple variables. In the old version we just cared about like the W0 and W1. That's all what we did. But now here Wj equals the Wj itself minus the learning rate, this blah blah, it's the same. Here it's Wj xi. What do we mean by that? Here, like for each parameter Wj and each xi yi, that means like for each x here, like xi of j, that means there will be like multiple features in like one example. Multiple features in one example. So this is the derivative, and it's gonna be for multiple features in one example. For example, like as we said before, the house is gonna have as example features uh, size, location, and building date. Okay. Now we're gonna talk about polynomial regression. By the way, I didn't tell you that. You see this gradient descent algorithm? Yes, it's really great if you understand it and like can implement it by yourself. It's easy. It's like easy algorithm if you are used to programming and building algorithms. It's really easy. But if you're not, don't worry. Like the TensorFlow framework and the R is going to do everything for you. Don't worry. Polynomial regression. So the point is, like, for example, here, for this point, we already talked about it, which is choosing the right fit to our data. So what if we said, what if we make it like a quadratic function for our hypothesis function, like that? This is a quadratic function, so it's gonna be like that, and it's really better fit to our data. But like, is it better for like the future? Because quadratic function is gonna be like that, and then it goes down like that. The quadratic function does that. But what if we had data here, for example here? It's gonna be bad, really. So what's the solution? Maybe if we make it as a cubic. Oh, sorry, this is not quadratic, this is cubic function. What do we mean by cubic? Like there is until x cubed. For the cubic function, it's like that, and then it goes up. That means if we have data here, the cubic function is better than the quadratic function. So as I said before in previous videos, the better you choose the function for your model that you're gonna fit your model to, the better your results gonna be, and it depends on your choice. So the point is choose your function according to the given data for your specific task. Normal equations. So we can get, now this is like gonna be funny. Why? Imagine that we can actually get the values of parameters that we want to learn, W, that minimizes JW, that give us like the minimum possible value for JW without any gradient descent iterations, without calculating anything, just by doing that, like x transpose x, like x transpose multiplied by x, inverse, we studied the inverse in our linear algebra review, multiplied by x transpose multiplied by y. So by doing that, we can get directly the set of W that minimizes the J. So yeah, you're gonna say, but there is a problem. What if we cannot have an inverse for this? You remember when we had like an experiment on Python and we found the like a singular matrix, and we said we cannot calculate a transpose for that matrix. There is two solutions for that. For example, the first solution, actually there is two problems for that you have to solve. You might have done one of two problems. A redundant feature. What do we mean? For example, age, like if you have like features to describe a person, and you have the age of that person and the year of birth. They are linearly dependent variables, the age and the year of birth. Like the higher the year of birth goes, the higher the age goes. So it makes no sense to have them both together. You need to remove one of them. Number of features is more than number of examples. That means if you have like, for example, 10 examples and 15 features, like 15 x's and only 10 examples, like xy tuples. So it makes no sense. Of course, you need way more examples than features. So this is two solutions to, if you have like a singular matrix, you can do these solutions so you can get like a calculable W. So now you're gonna ask, okay, but we learned gradient descent for what? I mean, this looks better. I mean, it's faster, definitely. So what's the problem with gradient descent? Actually, you use this like if you can see here, x transpose x is really expensive, especially with the inverse. X transpose x inverse is really expensive function. And if you have a lot of examples, like maybe hundreds of thousands, like, and sometimes millions of examples, it's gonna be really hard to calculate this. So it's better to use gradient descent. Gradient descent is gonna be better for you. But if you have like not that much, not hundreds of thousands of examples, and it's like less computationally expensive, you can just use the normal equation. So this is the rule. If you have too many examples, like million example or something like that, just use gradient descent. If you have less than that, use the normal equation. Okay, that was our video this time. It was shorter than the last time. I hope you understood well. If you didn't, just try to go back to the previous video, try to understand it well, and go to this video and then try to understand it slowly. Thank you very much and see you next video.